Alright, gang. This is obviously section 4.4. And it's the final section of Unit 4. And I guess the time has come, like a lot of chapters in mathematics, the time's come for us to solve equations involving these functions. So we've graphed them and evaluated them and done different kinds of things, converted, but there's obviously equations involving x or whatever variable that are exponential in nature or logarithmic in nature, and we're going to see how these things get solved. Okay, so part 1 is going to be about solving exponential equations. And obvious question, how do we do it? And so here's the steps. If you need to pause the video in order to have a chance to jot these down, then go ahead and do that. But we're going to dive right in. And if you had a chance to really think about the steps and not just mindlessly jot them down, all right, one of the steps involves taking the natural log of both sides. Now, it probably actually said in the step, yep, right here. If you remember the power rule, when we learned about the properties, the power rule says that we can bring the power down in front. And that's going to be really, really, really useful when we're looking to solve for x, because a rookie or someone that doesn't know any better or didn't know any better would probably look at this equation, and if I said, what's x? Solve for x. They might look at it and go, well, if it was 4 to the x is equal to like 16, I could tell you an answer, but 4 to the what power equals 15? I don't think I can really do that, especially when what you're probably most used to doing, or like your instinct at first when you're told to solve for x, is to try to like work the equation to where you can just get x by itself. So that's something that that's also what you might think about when you look at this equation, is how the heck am I supposed to get x by itself when it's up here as the exponent? And the answer is, like the steps say, and like I said, take the natural log of both sides, so that we can exploit that property, that power rule, which says like, oh, now that it's a natural log of 4 to the x power, I can bring that x down. Okay? Isn't that clever? So, a couple quick comments. Yes, you can take the log of both sides, or the natural log of both sides, just like you're allowed to multiply both sides of an equation by the same number, add the same number to both sides of an equation, subtract. So everything you used to do, take the square root of both sides of an equation, right? You can take the log of both sides. That's a legal thing that you're allowed to do. And the other thing you might be wondering is, why the natural log? Would you be allowed to take a quote-unquote normal log of both sides, like log base 10? Yeah, totally. But there is a certain situation where it's just highly recommended that you make it a natural log. And I'm going to see that over here, spoiler alert. When there's an e involved, you probably really want to make it a definite thing to make it a natural log of both sides. Now, I know there's no e in this equation, but you know what? In my mind, it doesn't really make any difference what kind of log with what base you take, both sides of. So I figure, since there are times where you really would find it advantageous to make it a natural log, let's just make it every time we take the log of both sides, we make it a natural log. So anyway, time to move on. Now that we've taken some kind of log of both sides, that means we can bring the x down, and now we're in a position to get x by itself. So how are we going to get x by itself here? Wouldn't we just, divide both sides by the natural log of 4? Okay? And so what we get for x is the natural log of 15 divided by the natural log of 4. Now, it's time for me to interject something important, I guess, and tell you that this would be, if you were looking for an exact answer, okay? If what was on the table was about finding an exact answer, this would actually be a good final answer. But if what you're looking for is an approximated answer, well, now you just go to your calculator, which has an ln button. Natural log of 15, close the parenthesis, divided by natural log of 4, close that parenthesis just for good measure. And what my calculator says is about 1.953, which makes sense, right? 4 to that power would get you 15, because if it was 4 to the second power, it'd be 16. But again, this would be exact, and this would be approximated. Now, quick experiment. What if you had taken a regular log of both sides, like log base 10? Then your final answer would have been that, log of 15 divided by log of 4. Well, quick little experiment. Your calculator also has a log button, log base 10 button. I want you to do the log of 15 over the log of 4 right now. And you're seeing that you're also getting 1.953-ish, right? So it doesn't matter what kind of log you take of both sides, whether natural log or log base 10, you're going to get, so this is also a good exact answer, but you should get the correct answer no matter what. So moving over to the second example, it's time to bring up the first step from this page, where first you need to isolate the base and exponent on one side, if necessary. See here, it wasn't necessary because, it was going to work out good from the start, where if I took the natural log of both sides, I would be able to apply that power rule property and bring the x down. If I take the natural log of both sides of this equation as is, I don't think the power rule would apply. If I took the natural log of all of this, I would not be allowed to bring down that 0.6x. It just doesn't fit the power rule. So that's why there is a step 1 of isolate the base and the exponent first, which means like I'm going to have to isolate the e to the 0.6x power by adding 3 to both sides and then dividing both sides by 40. And now it would be time to take the natural log of both sides. And even though you're probably still writing this stuff down, I want to kind of pause right there and point out that yes, if you now went ahead and went through the whole process of bringing the 0.6x down, you'd be fine because the power rule does apply now and you can bring that power down. But since it's an e to the 0.6x power and since it's a natural log, and what if I were just to ask you, what is the natural log of e to the 0.6x power? It shouldn't take you too long to come up with just 0.6x. The natural log of e to the 0.6x power is 0.6x. But again, I want to reassure you that if that didn't occur to you, and you were just going to like bring the power down and then divide both sides by the natural log of e, things would totally work out, right? No problem. But from here, how do we finish getting x by itself and solving for x now that we're in a position to get x by itself? Well, of course, we would just divide both sides by 0.6. And so that would be what an exact answer would look like, but our calculator would be able to approximate that for us. Natural log of 6, make sure to close the parentheses if there are any on your calculator. Then divide by 0.6. And make sure that you're able to get this on your calculator. About 2.986. And that's the second example. And now we're going to move on to this example. All right. So the question is, do we have to do any isolating, or can we just take the natural log of both sides right away? Like if we took the natural log of the left side and the right side, would we be able to apply the power rule and bring those powers down? The answer is yes. We can take the natural log of both sides and bring those powers down. But I want to point out that these parentheses around the x minus 2 and the 2x minus 3, totally necessary. Totally necessary. Because, we're bringing the entire x minus 2 down in front of the natural log of 5. Not just the 2 and not just the 3, it's the entire 2x plus 3 that we're putting in front of that natural log of 4. Now, as we look to move on, and eventually, again, now that we've brought down those powers, now that we've gotten these x's down to where we can actually solve for x, now we're going to just do whatever it takes to solve for x and get x by itself. So what do you think we're going to do next? I say we distribute the natural log of 5 through that bubble, and I say we distribute the natural log of 4 through that bubble. And we get x natural log of 5 minus 2 natural log of 5 over here equals 2x natural log of 4 plus 3 natural log of 4 over here. After we do that, and we get two terms over here and two terms over here, where one of the terms has an x over here and one of the terms has an x over here. What we're going to do next is we're going to get the terms that have x to the left side. So let's not do that color. So, hey, I pressed red. So we're going to move this term over here so it can be with the other term that has an x in it, and which means we're going to move this term to the other side. Again, we are separating the terms that have x in there from the terms that do not have an x. And we're going to get that. Okay, so you see how we've gotten the x's only to one side. But what's going to happen next on our quest to solve for x is we're going to, that's right, factor out an x. Oh, I knew it. Anyway, that's a 5. You can. Those are obviously 5s over there. But yes, we've factored out a common factor of x, leaving this bubble in there. And now we're getting so close to getting x by itself. All we got to do is divide both sides by this bubble and get this. And believe it or not, this is how you would leave your answer if you were looking for an exact answer. But let's say you were looking for an approximated answer. All you would need to do is throw this all into your calculator, but you're going to want to include parentheses there and there, and your calculator might, have its own parentheses kind of all there. So here I go in live time. Parenthesis 3 natural log of 4, close that, plus 2 natural log of 5, close that, then close the entire numerator, divided by left parenthesis natural log of 5, close the 5, minus 2 natural log of 4, close the 4, and then close the entire denominator. And what I'm getting here, go back to that color, is approximately negative 6.343. Boom. Ooh. Getting tricksy. So, next example. Solve for x. How are we going to solve this for x? Well, maybe you can compare this to just x squared minus 4x plus 3, and what would you have done if it was x squared minus 4x plus 3 equals 0? How would you have worked and started on solving that? And the answer is factor it by unfoil. So, bottom line, this unfoils to these two bubbles because this unfoils to this. So we can kind of use this as a guide. And what do we always do after we factor one side with the other side equal to 0? We set both factors equal to 0. And now we can work on solving each one separately by doing this. And what we've just done is set ourselves up to finally take the what of both sides in order to bring the x down. Natural log of both sides. Okay? Both equations. So natural log of e to the x is just x. So natural log of 3 is natural log of 3. And natural log of 1 is equal to 0, which your calculator will verify, obviously. ln of 1 equals 0. But the natural log of 3, if we were looking for an approximated answer, is man, this does not want to click right. So, oh man. So natural log of 3 is about 1.099. Part 2. Now we're going to change gears and learn how to solve log equations. Okay, so quick recap. If you're solving an exponential equation, you're going to, sometimes you have to be clever, but eventually you're going to need to take the natural log of both sides in order to bring the variable down in order to get it by itself. So here's the 3 basic steps to solving log equations. Step 1, isolate the log expression on one side. That's very similar. Step 2 is the money step, and it's convert to exponential form. And step 3 is going to be solve for the variable. So pause the video and get those down if you need to, but let's see those steps in action. Example A. Let's solve for x. Well, do you think the log expression is isolated? Or in other words, do you think we're in a position to translate this or convert it to exponential form as is? The answer is yes. Using our skills we learned earlier in the unit, let's convert this. Base of 4, logs of powers, and then equals x plus 3. So we've converted it to exponential form. And just like that, take a look at what we have now. Isn't this going to be super easy to solve for x? 4 squared is 16. Oh man, this is like going back to 5th grade or something. Solve for x now. Subtract 3 to both sides, of course. We've done this a million times. And the final answer is 13. But. I might as well bring this up now. In class, I most likely have mentioned that logs have a restricted domain. Like, you can't actually take the log of anything, you know. So that's why, like, when you get an answer for x, you got to be at least a little suspicious that x is actually allowed to equal 13. So if x were to be 13, then this entire input here would be 13 plus 3, 16. Are you allowed to take the log of 16? The answer is yes, of course. Remember, the only things you're not allowed to take the log of, like you cannot take the log of 0, and you cannot take the log of anything negative. So be aware of that as you get these answers. You have to just double check that they actually are, you know, legal, allowable answers. Anyway, let's move on to example B. Can we translate this or convert? I keep saying translate. Can we convert this as is? And the answer is no, because of the 3. Hence the first step of first we need to isolate. So how are we going to isolate the log part? Well, just simply divide both sides by 3 and get the natural log of 2x equals 4, because 12 divided by 3 is 4. And now we can convert. The base, of course, of this log being e, so e to the 4th equals 2x is the conversion to exponential form. And now we are in a great position to just get x by itself by dividing both sides by 2. Right? And so that would be an exact answer. But if you were looking for an approximated answer, we can do that also. E to the 4th power, all divided by 2. This is weird writing it backwards. But that's about 2 point... Oh, nope, I misread that in the... It's not very bright in my room right now. So 27.299 would be the approximated answer. Next example. Ooh, we're nearing the end, I do declare. Yes. Last example. Oh man, what do we do here? Are we in a position to convert this to exponential form? I don't think so. Whatever could we do here? We have a log plus another log. Can we do something with that? Oh yeah. We can smush them together, aka condense them together, using one of our handy-dandy properties, the product rule. So log plus a log, we can bring them together with the product rule and get this. And now we're in a position to do the, well, we're in a position to convert to exponential form, because base to power, okay? And, ooh, it appears that I've also at the same time distributed the x. Why have I done that? Well, because I have the benefit of experience and, I kind of know that it's going to be necessary. So it will be necessary, and I'm sure you'd realize that eventually, because the next step is to solve for x, right? Like once you convert it to exponential form, the idea is it's now very, very, very doable to solve for x. So if it was just x times the bubble x minus 7, that'd be great if it was equal to 0, but no, so what we're going to have to do is distribute the x and get x squared minus 7x, and then get everything on one side, which means like set it equal to 0. So 2 cubed is really 8. So what I kind of did was I subtracted 8 to the other side, but then I just kind of like swapped left side and right side. And so instead of it saying 0 equals x squared minus 7x minus 8, I'd rather it say x squared minus 7x minus 8 equals 0. Okay, now how do I solve this for x? I can't just get x by itself, hence why I've set it all equal to 0, so I can do what? What do you always do after you set something equal to 0? That's right, you factor. And what do you always do after you factor? You set both factors equal to 0. So you can solve them separately by adding 8 to both sides and subtracting 1 to both sides. So we get x equals 8 or x equals negative 1. But as I forgot to do in the second example, you need to just really quick double check if your final answer is allowed to be there. So if you plugged this number in for x, would that cause anything illegal? Nope. If I plugged 8 in for that x and that x, would it cause anything illegal? 8 minus 7. Now you can take the log of 1, you can take the log of 8, so this one's good. But if we plug in negative 1 for that x and also that x, it doesn't make any sense to take the log of negative 1. That's not a thing. And if that was a negative 1, you'd be taking the log of negative 8, which is also impossible. Once again, it's impossible to take any log of 0 or anything negative. So this is actually not an answer. Both good? No, we already did that. This one's good. This one, not so much. So don't forget to do that every time with logs, because once again, you can't take the log of anything. It's got to be something positive. Done.